Alright guys, today we got similar polygons, and then also we got some proofs here at the end. So a little bit of review on some of the vocab. We have ratio, comparison of two values, written as A over B or A to B when you use the colon right there. So scale factor, the ratio of the corresponding segments of similar shapes, written as the ratio of the new to the old. And it's really important that we write it as new over old and not old over new, because that affects how the scale factor is. Um, the reduction is a scale factor, and it's when your scale factor is between 0 and 1. So it's the new figure is smaller than the original figure. So like for example, if the ratio between the sides of a new figure, if you're like new is 1, but then your old was 2 right there, that's 1/2, and that's a reduction in size. And then enlargement, you could do like something like maybe like 3 to 1, like maybe you're triple in your side, so your scale factor is greater than 3, so it's an enlargement. Then also we have proportion. That's an equation that states two ratios represent the same value. We'll see some of those come up here in a bit. So similar polygons, you probably learned a little bit about this in middle school. All the angles are going to be congruent. And then corresponding sides, we're going to say that the sides are proportional. And a lot of people want to say the sides are similar, but that's probably not the best word. The best word is proportional, just in case that comes up on a quiz or test there. So anyways, looking at this next example here, right, the pairs of congruent angles and the extended proportion for the ratio of the corresponding sides. So this is pretty straightforward here. They tell us that polygon ABCD is similar, this little sign right there, little squiggly guy there, that is similar. So it's kind of like a congruent without the equal under it. So it's similar to TUVWX. So all the angles are pretty straightforward. It's angle A congruent to angle T. You should get all these here real quick. Angle B congruent to angle U. I'm just looking up here at these individual pieces, A and T, B and U. So you can go and get them all there. Angle C congruent to angle V. Angle D congruent to angle W. And angle E, is congruent to angle X. Okay, so remember all of our angles in similar figures will be congruent, and then like we said, the sides are proportional. So here's what I'm going to do here. I'm going to look at side AB. That corresponds with TU. So we have AB and then TU. Alright, other sides that are corresponding, you can go BC right there. I guess I'll just use one line there. So BC corresponds to UV. And we have CD for this next one. It's proportional to VW. And you can keep kind of going all the way around. You can use different colors if you want, so I don't have to have 10,000 lines. We have ED, that is proportional to XW. And then you got, last but not least, this AE and then TX. Oops. So we have AE and then TX. So those ratios, what it means to be proportional, it means all of these ratios need to be the same. Every single one of them. That's what it means to be proportional. Okay. So we'll deal with some actual numbers here on this one here. So like, are these polygons similar? If they are, write a similarity statement and then find the scale factor. Okay, so since they're wanting us to find the scale factor, I'm going to strategically start to write these as my new over old figures right here. So I'm going to take the new side over the old side, and then automatically I have my scale factor rocking and rolling there. And then we're going from figure X to figure Y. So we're going to assume figure Y is the new figure. Typically, if they don't say that, typically I say the left figure is the old, and then the right figure is the new. So I'm going to look here for this 6 right here, and what I like to do when I'm dealing with the side lengths and trying to figure out which sides match up, I always say the shortest side should match up with the other shortest side on the other figure. So that would be the 3 over there on ABC. And then if I go and look at like the medium length side, there's 8, and then there's 4. And we got to go and determine if these are all the same ratio. You have 10, and then you got 5 right there. So every single one of those reduces down to 2 over 1, or you could just say 2. Okay, so that means the scale factor, sometimes we use SF, that's going to be 2. That means each side is being doubled. If I double 3, you get 6. If I double 5, you get 10. If I double 4, you get 8. That's how the scale factor works. The scale factor is what do you need to multiply everything by to get your new figure. Since all sides are proportional, then we say that these are similar. And it also asks us to write a similarity statement. So I'm going to write this above. I'm going to say ABC, the triangle ABC is similar. There's that little squiggly guy again. And then FDE. And actually I need a little triangle. Bad notation there. But that's pretty much it. You just got to check all of your different ratios. So let's try this next one here and see what's going on. Maybe something similar, maybe different, I'm not sure. So look here, here's your longest side, apparently is 9. So we're going to go, and actually I need to do new over old. Sometimes I go a little too quick and forget about that. So we want to go 6 over 9, since we're going from this figure to this. So 6 over 9. We need to compare that with, now check this out, you got 6 matching up with 4. And then all the other ones happen to be the same. 6 over 4, 6 over 4. Now if you reduce all of these fractions, these are all going to reduce down to the same fraction. It's going to be 2/3. So that is actually your scale factor there. Your scale factor is 2/3. And then you can write your similarity statement. That's pretty much all you got to do on these. So let's see, I guess I'll go GHIJ is similar to, and then we'll go KLMN. That's how to do that one. Now every now and then they'll try to throw you off and rotate an object, or maybe use slightly different numbers here. So here's what I'm going to do. I'm going to go take my longest side, 6, and I'm going to compare that to the longest side of figure X right there. So we have 6 to 8 right there. Alright, now I need to go and compare that with the shorter side of the rectangle, 3 and 6. Now if I look closely at these here, the 6 over 8, that reduces down to 3/4. Okay, but the 3 over the 6, that reduces a little differently. That reduces to 1/2. So these right here are not equal, so therefore the sides are not proportional. So these sides are not proportional, therefore we can't write a similarity statement. That's because the fractions right here are not the same. Okay. Now if I'm looking here at this last example, the same type right here, notice you got all these different numbers going on here, and initially, I see an 11 and a 10, and then I see a 11 and a 12, but then this one's 10 and 12, so it's kind of weird with some of the numbers. So this goes back to what I was saying. Start with, maybe your shortest side, so on triangle X, it's 10, and then compare that to the other shortest side. All right, so right now we got a 10 to 10 ratio, okay, which reduces to 1. Let's see what the other ones look like here. So next longest side is 11. Compare that to the next longest side of Y, that's also 11. So notice that those are equal so far. Look over here at 12, you got 12 and 12. Notice those reduce. Those are your corresponding sides. Those all reduce down to 1 over 1. So that means your scale factor in this case is equal to 1. That means you're really not changing anything. It actually means that these are congruent figures. Okay. Now since they're asking for a similarity statement, I'm going to go triangle ABC is similar to triangle, and then I'm looking here, it's marked with 3 ticks, so we need to go over there and look at F. So that starts with F, it goes next to D, and then lastly we have E. So there you go. Okay. Last few here. Oh, okay, now in this example here, we're going to talk about, in the next lesson, we talk about the means and the extremes. And typically we say, like, the means are the things, the means are where you have like two of the same thing. So we say A and A should be the means, and then the C and the B are the extremes. That we don't really use that until tomorrow's lesson, so just kind of hold off on that, or maybe come back to that, once you go through tomorrow's lesson. Okay, but jumping back into a different example, look at this here. It says solve for the value of D if the AB to AC ratio is 15 to 8. We need to somehow incorporate that 15 to 8, and that apparently is a ratio of these two sides right here. So remember, it's AB right here, this side 60, and then to AC, which is the 3D plus 2. So notice here how everything kind of corresponds. The AB corresponds with the 15. The AB also corresponds with the 60 from the figure. Okay, and then we'll correspond the AC corresponds with the 8. So the AC also needs to correspond with the 3D. Oops, kind of looks bad there. 3D plus 2. And then there you got a proportion. All right. Now in this one right here, to solve a proportion, you need to, dropping stuff. You need to cross multiply and divide on these here. So we're going to go 60 times 8. And then equals 15. And then here's an important thing. Go put parentheses around this. This is called a complex proportion. That's when you have a binomial in the numerator or denominator. So we need to throw some parentheses around that right there. Okay, because essentially what we need to do is multiply 15 times 3D and 15 times 2. Okay, so then we have 60 or 6 times 8 right there. So 6 times 8 is 48. And then you got that extra 0, so I'll put that there. I'm seeing 45D and then plus 30. Okay, and then we'll subtract 30 from both sides. You get 45D equals 450. And then divide, and you should get D is equal to 10. And then let's double check, make sure they weren't asking for anything else. Yeah, all they were asking for was what D was. So we're good there on that. Now sometimes they're not going to give you the ratio. You're going to have to take two figures and figure out what the scale factor or what the ratio is here. So notice here you have two similar, trapezoids in this case here. And they're asking for the value of x. Okay, so if I'm trying to find this side x right here, that corresponds with this 7.5 on the bigger trapezoid. Now, you got to be kind of strategic about what you do or what you use for your other fraction, because you need two numbers, right? You need at least two numbers so you can solve this proportion. So I look for two sides that are given on both figures, and I see that 6 on for DE on the smaller trapezoid, and then we see the 9 for that full length on the larger trapezoid. So notice here I got the small over the big for the trapezoid, so I need to go small to the big on the other trapezoid. So kind of like that right there. Okay, and I'm going to use my calculator for 6 times 7.5. Apparently that's about 45. And then equals 9x. So then when you divide, I guess you get x equals 5. Now they didn't ask us to do it, but we can also use a ratio to go find y eventually. So they have y here. I'm going to go ahead and just run through that here real quick. You're still going to use the 6 and 9 ratio, but then you have to use a totally different side for the 5 right there. So we can say, what is that, y over 5 right there. Then we'll cross multiply and divide. That would be 9y, I guess, equals 30. Divide both sides by 9. You can say 30 over 9. And then I guess we could reduce, both of those are divisible by, I guess, 3 right there. So then we can say that's 10 over 3 for your y value. Okay, so that's kind of I guess that's the first half of this lesson here. The second half of this lesson is about proving triangles similar. Okay, and it kind of uses some of the same elements that we just did. So this first one here, if two angles of a triangle are congruent to the angles of another, then the triangles are similar. So this is the angle-angle similarity postulate right here. All right, so here's how it typically looks. You have two sets of angles marked congruent right there. And then automatically, you know, the third angle has to be congruent as well. So then we say these are similar figures right there. Okay. Now, side angle side looks a hair different here. And to help myself, I'm going to label these ABC. And then I guess let's go X, Y, Z. All right, so for side angle side similarity, it's kind of it's a weird way to mark it. We don't have like a good symbol for similarity, so we're going to say this side AC is similar, or it's proportional. I guess I need to say it's proportional to XZ, and then we'll say, oh, whoops, I didn't mean to do that. Side AB is proportional to side XY right there. All right, and then since they're saying it needs to be in this SAS mindset here, we got to say that angle A is also congruent to angle X right there. And that is what that means there. Now, sometimes instead of saying that the sides, like marking that they are proportional, they'll actually write out the proportion. They'll say XY over AB is the same ratio as, I guess, XZ over AC. And that's how you write out that two sides are proportional. They have the same ratio between them. Okay. Now this last set of triangles here, this does the same thing here, except it's side, side, side. So you're going to have three sets of sides being similar. So actually I'm going to do the whole same thing that I just did there. I'm going to write out my ratios. So let's see here. So we'll say it's side AB. Let's assume that's the side that matches up with X, Y. So we'll say it doesn't matter, unless you're doing scale factor, it doesn't really matter which one you write over the other. So I'll just use those right there. I'll go AB, X, Y. Let's say that matches up with BC and YZ. And then the last set should also be proportional. So we'll go AC and then XZ. And that's how you would mark it right there. You really don't have a marking, and that's how you have to write out that the sides are proportional. Okay. And so if you have three sides that are proportional, then they are similar. And we've already kind of done examples where we checked and see if all the sides are proportional. If the sides are proportional, then they are similar. And this is, you know, the theorems we just learned, the postulates we just learned, are dealing more with the triangle specifically. So this next section here, we just go and determine, do we have similar triangles, do we not? Okay. So this next one here, so notice here that you're given two angles on one triangle and you're given two angles on another triangle. Some people will say, well, those two angles don't actually add up, or match up, I guess I should say. So what we need to do is actually, what I tell my students to do is go find that third angle. So remember, all angles add up to 180. So if you add 77 and 48 and then subtract them from 180, you should get 55. And then notice here, you got 48 and 55. You got 48 and 55 on the other triangle. That means this last angle over here by D has to be 77 degrees. All right, and then since you have those right there, we can say by angle similarity postulate right there that these triangles are similar. And then let's go ahead and label the correct ones here. So we'll say A, B, C, I guess, is similar to triangle, I guess, D, F, E. Okay. Let's look at this next one here, what we got going on. So some people are going to want to look at the ratio of the sides right away, and there's nothing wrong with that there, except we don't really know what AF is, and then we don't really know what CT is. Okay, even if the sides were proportional here, it's not written in that format where it's SAS. Okay, it has to be SAS if they're similar. You can do SAS, you can do SSS for side, 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 and then angle, angle, but no other ways to actually prove triangles congruent. So I'm going to say these right here, these are not similar. Okay, now, once again, you can go check the scale factors if you want, but I don't even think those are going to match up anyways. So it doesn't even matter. So it's not similar, it's not SAS, so we're good to go there on that. Okay, let's look at this one. This one's kind of like the one right above it where you got multiple angles here. So I'm going to add up 92 plus 57 and then minus 180 there. And that gets us 31 degrees. Okay, so now that's looking like it's not going to match up with the other triangle, because if you go 92 plus 41 and then subtract from 180, that gets us 47 instead. So obviously different numbers right there. So this one right here, it's not similar. Okay, and that's because none of the angles match up. Now 10, initially when people see 10, they want to say, well, these are not similar because they don't have anything that matches up. They might say, well, okay, maybe the two triangles both have angle A, but they don't have any other things that match up. And here's the key thing: these little triangles right here that are filled in, that tells us an important piece of information. That tells us that the two lines are parallel. If the two lines are parallel that are on a common transversal, you can say these corresponding angles, these angles that match up, are actually congruent. And you can do that on the other side over here by angle D and over here by angle E as well. So we can say that these are similar by angle-angle similarity postulate. And then we can say, I guess, triangle ABD in this case is similar to triangle, and it also uses A, it's ACE in that case. Okay. Alright, a couple more kind of similar. Number 11, notice here on this triangle EFD, notice that none of the other, you only got one angle. Okay, so some people say, well, hey, once I add these angles up, that angle right there is 43. And so, well, okay, those match up. But you need two sets of angles that match up. And they don't tell us anything about E or F. Okay, so since they don't tell us anything about E or F, it's kind of like we only have one angle. We need at least two angles to be congruent. So this one right here, we just say these are not similar. Not similar because there's only one angle. I guess marked on both. I'm just going to write one angle marked. Okay. 12 is kind of a special one here. Alright, so notice here, there's two ways you can think about it. Let's say all of these sides, I don't know what they are, but let's say they were all like 5, I guess. And then maybe all these other sides were all 10. We could say, well, these all have a 10 to 5 ratio. I'm kind of running out of room in there, and I can't even write. Let's try that again. 10 to 5, which is equal to 10 to 5. All of those are the same ratio. So one way you could say that these triangles are similar is by side-side similarity. Now also, if we use the whole idea that we have equilateral triangles, we can also think about, hey, we have also automatically equal angular triangles. That means all of your angles have to be congruent. These all have to be 60-degree angles. So you could also say angle-angle similarity. So there's two different ways to look at 12 there. That one's a little weird on that. Okay, regardless, I guess, really we can say the triangle, it doesn't even matter because all the angles are congruent to each other, so you can just say CMT is similar to whatever angles you want, and SAR, I guess. I think that's supposed to be an R right there. But anyways, it doesn't even matter. All the angles are congruent, so all the angles match up no matter what order you do it in. So those are kind of funky cases there. Now we got a few more here. Number 13. Let's see here. So notice with this one we have two sides marked congruent. Okay, so then therefore these angles have to be congruent right here. This is an isosceles triangle. So therefore, if those are both isosceles triangles, oh, okay, well actually, okay, so yeah, these are isosceles triangles here, but now I'm looking at it, we don't know if these angles are congruent to each other. It's about to say angle, angle, but we're not sure if the sides, or I'm sorry, if the angles are actually the same, so we can't use our angle-angle approach. Now, we can use the fact that these sides should match up, and let's check the scale factors of each one. So we need to actually physically check this here. So I'm going to check the side 6 right there, can check that with the side 4. And then we need to check the 9s with the other legs. So the 9s with the 6s. Alright. And then whenever we reduce all those fractions, I believe those both go, or all of them go down to 3 over 2 right there. So we're going to say these are similar by side, side, side. So if I go in the order of triangle ABC, I need to start with X, but then I guess it doesn't matter if you go Y and then Z. It doesn't really matter on the order. This is, B and C should correspond with Y and Z. Now 14, this is, I was kind of getting ahead of myself here. 14, notice you do have isosceles triangles, but then notice here, they tell us that this angle over here is 30, so those obviously match up. So that means the two base angles of your isosceles, if it'll let me draw here, these two sets of angles are actually all congruent to one another right there. So with these here, you can say angle-angle similarity, and I guess we'll go triangle NMO is similar to triangle Q, and then P and R are both congruent, so it doesn't really matter on the order. So you can, change it up there if you want. And that is it there. So all that stuff we just did, we're now going to incorporate into our proofs here. So we got a couple of these happening right here.